Acid-base equilibrium, relative strengths of acids and bases. In this tutorial, we will be going over the properties of weak acids and weak bases, determining the position of equilibrium in an acid-base reaction, acid strength and number of oxygen atoms on the central atom, acid strength and the location of valence electrons on the central atom, and then some work examples at the end. Properties of weak acids and weak bases. Weak acids only partially ionize in aqueous solutions. They exist in the solutions as mixtures of acid molecules and their constituent ions. So in this case, at any given point in time, we will have both hydrofluoric acid molecules and hydrogen ions and fluoride ions. Weak acids will also have a double arrow, as represented right here, in the equation to indicate that the reaction is reversible. The conjugate base of weak acids show a slight ability to remove protons from water. The conjugate bases of weak acids are weak bases. So an example is carbonic acid, which is a weak acid, reacting with water, which is a weak base, to form the conjugate acid of the water and the conjugate base of the carbonic acid. Substances with negligible acidity. Species that contain hydrogen but do not demonstrate any acidic behavior in water. An example of this is CH4, which is methane. Methane has extremely low acidic behavior due to the fact that it's very difficult to remove a hydrogen from methane due to differences in electronegativity values. Conjugate bases of these species are strong bases reacting completely with water, forming hydroxide by pulling protons off another species, typically water. An example of this would be CH3-1 reacting in water to form methane and hydroxide ions. In this situation, the water is going to donate a proton to the CH3-1, and the CH3-1 is going to form the very stable form of methane. So CH3-1 is a strong base, and the methane molecule is very stable with the production of hydroxide ions, making this a basic solution. So the more easily a base accepts a proton, in other words, a strong base, the less easily its conjugate acid gives up a proton. Determining the position of equilibrium in an acid-base reaction. In every acid-base reaction, the position of equilibrium favors the transfer of a proton to the stronger base or the removal of a proton from the stronger acid. The position of the equilibrium favors the reaction of the stronger acid and the stronger base to form the weaker acid and the weaker base. We'll look at some examples of that in a moment. The equilibrium mixture will contain more of the weaker acid and weaker base and less of the stronger acid and the stronger base. Helpful hints. As soon as a weak acid or weak base is identified in the reaction, that is the side that's favored. The hydronium ion, H3O+1, is a stronger acid than any identified weak acid. The hydroxide ion, OH-1, is a stronger base than any identified weak base. Let's look at an example. Here we have HF plus H2O yields F-1 plus H3O+1. When we're trying to figure out where to start, always look for either hydroxide or hydronium. So here we have hydronium, and that hydronium is always going to be the stronger acid. So if H3O+1 is the stronger acid, that must mean that the F-1 is going to be the stronger base. So that leaves the HF to be the weaker acid and H2O to be the weaker base. The reactant side is going to be favored because the K should be small in magnitude. Consider the weak acid HSO4-1 and HCO3-1. The electronegativity values of the central atom of sulfur and carbon are the same at 2.6. Let's start by stating the number of oxygen atoms in HSO4-1. So if we look at this ion, we notice that there are 4 oxygen atoms. Then let's state the number of oxygen atoms in HCO3 minus 1. Here we notice that there are 3 oxygen atoms. Then the next thing that we want to do when we consider these acids is identify the principal energy level containing the valence electrons of sulfur. Sulfur is in period 3, N will equal 3. Identify the principal energy level containing the valence electrons of carbon. Carbon is in the second period, so N will equal 2. We can use this information to determine which of these 2 ions is a stronger acid. So how do the number of oxygen atoms and the location of the valence electrons for each of these central atoms influence the overall acidity of the ion? The more oxygen atoms present on the central atom, the greater the tendency to pull electron density away from the central atom. This results in an increased ability of the hydrogen ion to ionize, resulting in an increase in acidic behavior. In other words, an increase in acidic strength. HSO4 minus 1 is a stronger weak acid relative to HCO3 minus 1 due to the sulfur atom of the HSO4 minus 1 ion having a greater nuclear shielding than the carbon atom in the HCO3 minus 1 ion. The labile proton in HSO4 minus 1 ionizes more readily than the labile proton in HCO3 minus 1, accounting for the increased acidic behavior in HSO4 minus 1 relative to HCO3 minus 1. Worked example. Let's look at our first example. HSO4 minus 1, CO3 minus 2, SO4 minus 2, and HCO3 minus 1. This is the example that we just went through on the previous slide. So we know that HSO4 minus 1 is going to be the stronger acid due to the differences in the number of oxygens and also the location of the valence electrons on the sulfur in comparison with the carbon. If HSO4 minus 1 is my stronger acid, that means that the CO3 minus 2 must be the stronger base. And of course it's going to be the stronger base because it does not have any type of hydrogens to donate. As a result, the weaker acid will be HCO3 minus 1 and the weaker base will be SO4 minus 2. State whether the reactants or products are favored in the equilibrium system. Because HSO4 minus 1 and CO3 minus 2 are our stronger acids and bases compared to the product side, we are going to favor the formation of products because we will always favor the side that has the weaker acids and bases. Let's look at our next example. HC2H3O2 reacting with water to form the hydronium ion and the acetate ion. We know from experience that HC2H3O2 is a weak acid, therefore the water has to be the weaker base. The hydronium ion is always going to be a stronger acid, and then the acetate ion will be the stronger base. So we can label this as weak acid, weak base, stronger weak acid, and stronger weak base. Therefore, this equilibrium system is going to favor the formation of reactants. HPO4 minus 2 and water, H2PO4 minus 1, and hydroxide. In this example, I'd be starting out with the hydroxide ion as my stronger weak base, which means the H2PO4 minus 1 has to be my stronger weak acid. As a result, the water is going to be my weak acid, and the HPO4 minus 2 is going to be my weak base. So in this situation, the reactant side will be favored because we are always going to favor the side with the weak acid and the weak base. Let's look at our next example. Ammonium ion reacting with hydroxide to form ammonia and water. In this case, again, I would always be starting out with my hydroxide ion, which is going to be my stronger weak base, which means that the ammonium ion has to be my stronger weak acid. As a result, the water will be my weak acid, and the NH3 will be my weak base. Therefore, we are going to favor the formation of products. Note, hydroxide, OH-1, is a stronger base than ammonia, NH3. Nitrogen has a lower electronegativity value than oxygen, as we see right here, with nitrogen having an electronegativity value of 3 and oxygen of 3.4. Nitrogen is less likely to hold onto the labile proton than oxygen. The hydrogen ion is more likely to ionize from an NH bond in an ammonia molecule than an OH bond in a water molecule. So what did you learn? We went over the properties of weak acids and weak bases. We talked quite a bit about determining the position of equilibrium in an acid-base reaction. We talked about acid strength and the number of oxygen atoms on a central atom, acid strength and the location of a valence electrons on the central atom, and then we did worked examples at the end. Need more help? Feel free to contact me. Have a great day.